Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So, anyways, just before I get started, I just want to remind you that Assignment 1 has been released. It is due by the end of February 2nd, but I must stress, like I may have mentioned in the past, I usually leave the assignment submission open until about 8:30 in the morning that next morning. So, when you look at this, it's really just 8:30 in the morning that next morning, okay? I like to just make sure that's available for any technical issues, like we seem to have had today with random powder outages here. Another thing, I will be posting, hopefully later today, assuming nothing strange otherwise happens today, a short summary video talking about Assignment 1, so that I'll give you the big kind of highlights about the assignment, but you should have enough stuff to start playing around with the first problem, okay? So I'm hoping that this will help reinforce a lot of the concepts that we've seen in the class so far. So other than that, make sure you do the onboarding quiz. It's an important thing to do for the proctor track stuff for the midterm and the final. So please just, if you haven't done that yet, I encourage you to do that. So anyways, are there any questions or concerns about what I mentioned just a moment ago, or are we good to go? Keep in mind, I'm always happy to answer questions before and after class, during office hours. Send me a message. I'm very happy to answer those kinds of things. Or if there's anything very specific I need to address for everybody, I'll try to do that as easy as I can. No worries, no worries. So I guess with that being said, why don't we get started, okay? So I want to recap something that I asked you to take a look at in the notes, just to talk a little bit more about where we sort of left off last time. So last time I was talking about how instead of thinking about our efficiency for an algorithm with a given computer, just like any one computer, like a laptop or say a smartphone or something like that, instead of thinking about efficiency with respect to just one machine, I want to think about it with respect to the algorithm itself. So what we do is we adopt a model of computation that's supposed to represent what we're trying to really look at. In our case, general sequential computers, typically, at least in this course. So what we do is we follow the rules for which we can analyze the algorithms using that model, based on how it functions. And like I said, the RAM model, the random access machine model, if you actually go digging around in your own curiosity with it, it should remind you a lot, if you were even just to take a glance at it, it should remind you a lot of assembly and the way assembly organizes instructions. So that's one aspect of the RAM model that should hopefully help kind of motivate some things that I talked about last time, where sometimes when we actually measure these operations out by constant number of operations, those can represent actual CPU cycles. And those constants can differ from one computer to another computer. So I want you to just keep that in the back of your mind, because it's rather helpful for some of the intuition for today, okay? Another thing I want to talk about is what I did at the end of class, where I start talking about how I can count the operations. So what I did is I went through the lines and I was counting them, right? So what I can do is I want to derive one of these complexity functions that can tell me about the efficiency of the algorithm for my kind of analysis. So usually in this course, we're going to be interested in worst case analysis. So I wanted to highlight a couple of ways you're going to find me commonly analyzing algorithms in this course. The former more often than the latter, but I want to show you both because, one, you can, of course, draw out a table and count up all the operations like I did in class. But I want to show you some ways that are a little less time-consuming. Why? Because you want to save yourself a little bit of time. So when you're say wanting to apply these methods, or you can pick one that seems appropriate for what you would like to do, if you want to draw out a table, or if you want to use this approach or this approach, I'm more than happy to see you try any of them. The one thing I do recommend is that take a look at the examples I have in the notes. It will give you a very good impression of what I'll be expecting from you for the assignment, okay? Just because we only have so much time here right now, and I wish I could just write out all of these in much more delicate detail with you. So anyways, I want to talk about like do I have to like make constants for all the lines for all my operations in each line, or even group all the operations of a same kind and count those? You can, but that's rather time consuming. Instead, when I have my pseudocode like this, we'll use a lot of the intuition that we would gain from doing something like that exercise with our table. So just as an example, I want to first show you just a couple of ways you can kind of really speed things up. You'll find I'll do this very often in this course. Is when I want to look at these operations, so here's the linear search, by the way. I didn't give it a title, didn't give it its header or anything like that. I have linear search written twice over here. So what I can do, instead of looking at each of the lines and say, okay, well, that's some constant times how long ever this takes, which it's just some constant number of operations, right? That's just an assignment, right? I will mention that based on some justifications I'm going to give you a little later, a constant number of operations may as well just be treated as a single step or a single operation. So you can even just count them directly like that. But you could just simply say, hey, okay, well, this is a constant number of operations, right? This if statement and this is all these are all just constant number of operations, right? Same with this else statement. This return right here, that's all a constant number of operations. So why don't I just say, okay, well, all of these, this, all of this takes some constant number of operations, right? All of these. So why don't I just point that out and just say, okay, well, all of these take some constant number of operations. Well, this assignment inside the while loop, that's some constant number of operations too. It's just an assignment with an addition operation, right? So I could take these and say, okay, well, that's some constant number of operations. So I'm going to call that C1. And I could call all of these ones C2. Because you'd agree with me, I'm hoping. If not, I'm happy to answer it. If I have a constant number of operations that all take a constant number of operations, you'd agree with me that that's just a constant number of operations, right? So that's how I'm grouping them like this, is I'm just taking all those constant operations that all take constant time, and I'm just grouping them all together. And you might ask, Dan, why do I have to like give them names like these constants here? You don't have to. I just find it's very helpful for when you're doing the analysis, because you can think of these constant names almost like I'm grouping and labeling them. That's another reason why this approach can be rather helpful for a reader. So somebody's like looking at this and say, okay, well, okay, so you're talking about this, this, and this. So I'm just saying all of those are a constant number of operations. They take C2 many operations, some constant number of operations. So now there's one other aspect to this that I have not really touched upon. It's this while loop here, right? Well, the question I have, and you can tell me in the chat or answer for me, if I were to tell you that this takes C1 times the number of iterations of this loop, what is the number of iterations for this loop? So like, how many times is it going to increment I by 1? In the worst case. Yeah, it's going to increment I n times, right? Now, if you want to be finicky about this, you're more than welcome to say, okay, well, technically it doesn't execute this line one extra time, but you can always see it's like, oh, well, yeah, well, there's this one time where it's going to check one of these two and it's going to fail, right? You can include that, but I'm really just going to care about how many times this C1 many operations occur, right? Because you'd agree with me that evaluating these two conditions takes constant time as well. So here's the cool part. It doesn't matter. It doesn't matter. So how many iterations are there for this line? Because I'm counting how many times this happens. Because I may as well have just said, okay, it's C1. This C1 is literally this, all of these, plus that. But keep in mind that if you were to break this out and say, okay, I'm going to count up how many times these occur, which this is some constant number, with one extra check. And then you go in here and you go, okay, well, I'm going to do this n times, right? Each with a constant number of operations. If you actually work out the algebra with this, the alphabets of math. If you're doing this, you'll find that you'll end up still with a linear function. It won't make any difference. And it's really neat like that. So you'll very often find that when I look at this, I don't really have to worry so much about it being n plus 1 versus n very often. So really, if I were to look at this, I could just simply say, okay, the number of iterations of how many times this line happens, it's just n, right? So if you were to write this out more delicately, you'd say, okay, this line, and this line all take a constant number of operations. You could give it a name, like C2, and say, okay, that takes a constant number of operations, C1. And you could simply say, okay, well, this while loop, in the worst case, has to iterate at least n times, right? So that means that total number of times C1 operations are going to occur is n, right? So you put this all together, and then you end up with a complexity function that looks like this. C2 plus C1 times n. Can somebody tell me what that is in big O terms? We will talk about big O today. I can tell you that up front. So if it's been a little while with big O, it's okay. We're going to talk all about big O today. Now, you would agree with me that's big O of n. Notice I get the exact same result. Now, that's one approach you can take. You'll find I'll very often use this one. Now, if you ever find yourself invoking as subroutines other algorithms, you'll find something I'm going to mention a little later more useful for kind of coming up with the complexity function. But if you ever find yourself dealing with more sophisticated parts of your algorithm, say for example, you don't really know what the constant is, you can always write something like, oh, it's big O of that something for this particular part of the algorithm. And then you just take whatever inside the big O notation and include that in your complexity function. Okay? So, for example, you may find this rather useful advice for when we start seeing some algorithms that use other algorithms. But I just wanted to point that out. Are there any questions about this approach? You'll notice that I'm not really like going through every single line in the same way I did before. Now I'm just trying to group them together by using less constants. Why? This saves you time. You don't have to worry. You're counting all the operations, but you're not like... Imagine if this was a way more complicated algorithm. This would take a very long time to do as a table, right? So if there aren't any questions about this, I'm going to proceed to talk briefly about this one. This is a more classic way I like to... when I taught analysis of algorithms very often, I would teach this technique. But for some algorithms, that approach I have over there is often more versatile. This one's more... It's usually very useful when you have algorithms with lots of loops in them, or nested loops. You have to be very careful, though. So here's the idea. What I usually call this the barometer method, or use of barometers. You may know of that term from weather. So here's the idea. You look at each of these operations. You'd agree with me that this assignment happens once, right? Just at the beginning. This if statement with all of this in here only happens once at most, right? This happens once at most. This while loop, it happens several times, right? In fact, in the worst case, it can happen n plus 1 times. But this line right here, that takes n times in the worst case. But notice that these two lines are the ones that happen the most over the entire execution of the algorithm. Does everybody see that? So what you can do is you pick one of the two lines that stick out to you like this. In fact, you can pick several lines and count those. Almost like you're putting, you know, in like if you pull out an IDE for programming and you have like a debugger tool that you set lines by your code for it to stop at breakpoints. I'm saying it almost in that same way, where what you do is right beside each of your lines, you'll say, okay, I'm going to count this one, I'll count this one, and I'll count that one. And then you just count how many times those happen. So this is more the drawback with this approach, is that you have to have some intuition about how the algorithm works. So in this case, notice that I could pick this line right here, this one. And you might ask, okay, so how many times does that line occur? Well, we already established that earlier. This happens n times. But notice that And I will give you there is a more detailed explanation in the notes, and I recommend you strongly look at that example. But here's the idea. You identify lines that happen more often than any other line. You pick one of them. And then what you do is you count how many times it happens based on the justification I gave you a moment ago. I told you that, okay, if these are some constant number of operations, and if you're familiar with big O notation, a little bit even, you'll notice that these constants get dropped. So this may as well have been a 1. That could have been a 1, right? Speaking about the big O notation, it makes no difference, right? Does everybody see that? That's a very important thing I want to point out. So now all you have to do is look at this and say, okay, observe that every other operation except for these two happens less frequently than these two, right? So you're going to count one of them as a single step. And how many times did the line I pick occur? N times. So you could just simply say, okay, well, this takes big O of n time. You can see how nifty and fast that is, right? Does everybody see that? But notice that it requires more intuition. In fact, you would have to justify to the reader that you could pick this line. So that's why I recommend you take a look at the example I have in the notes. So are there any questions about these two, or does this seem pretty crystal clear? So just to illustrate this principle, you could have, for example, 3 nested for loops, and what you would do is you'd pick the line in the furthest most instruction inside the nested loops. And you would just count how many times that happens. Are we okay with this? I just wanted to recap this because I asked you to take a look at it, but I wanted to make sure that I reinforced the main ideas from there. So if we're okay with that, give me 2 thumbs up if we're okay with that. Excellent, excellent. So now that brings me to talking about, I must also stress, I did mention this, but in the notes you'll find another example of doing this process with both of these, with insertion sort. You know insertion sort. So I recommend you take a look at that example. I show you how you could do this with insertion sort. So like I said, any one of these methods is perfectly valid for doing this. So if you're working on your assignment, if you like that approach, you can use that approach. If you like this, you could do this. If you like do a table, because the algorithm you're probably going to cook up is probably not going to be very sophisticated. Possibly. I don't want to say. But my point is that any of these are perfectly valid ways of counting all the operations. Okay? So why don't we head on over here? I'm going to kind of walk my way on over here. Wait. What we're going to do is I want to motivate one other element. Now, I told you that these constants that pop up, they're very often, they can represent actual CPU cycles. And those can vary between different computers. Now, another thing, and I'm not sure if you've seen this maybe in 210, but very often when you look at different algorithms, as the input size grows, there are points for which one algorithm, maybe for smaller instances, outperforms another algorithm, but there is some point for which one algorithm may eventually beat the other algorithm for any arbitrarily large instance. So we very often will see this. I'm going to include in the notes an example of one of these tables. I'm sure you've seen maybe one of these before. But my point is that very often when you compare these complexity functions between two different say if I give you 2 different algorithms and I get these complexity functions and I compare them based on their constants and so on, and I measure out based on the input size. As the input size grows, there may be a point where one algorithm suddenly starts dominating the other in terms of how much faster it is. So I want some natural way to represent both of the phenomena that I just described. This one about how we don't actually count the CPU cycles. Instead, we talk about them in terms of constants. And likewise, this trade-off that may happen between 2 different algorithms for a sufficiently large, or large enough, in plain language, size for the input. So that brings me to talking about so-called growth rates growth rates of functions. Now, for some of you, this may be like, oh man, it's not this again. But we will talk about this for a couple lectures. What I'll refer to as growth rates of functions, or asymptotics. You might ask, what does that mean? We're looking at the behavior of functions as the inputs of them get large. And you might say, okay, well, how are we going to do that? I'm going to talk about big O first. We're going to talk about some other so-called asymptotic notations in a little bit. But here's the idea. So first, let's talk a little bit about big O. Now, you may or may not have seen in 210 the formal definition for big O. I'm going to talk about it, and I'm going to expect you to understand it after playing around with it, say on the first assignment. But we're going to see plenty of examples of how we can use these notations. So I'm going to first give the formal definition for big O. First, is everybody excited? Is everybody excited about hearing about big O? Has anybody ever seen the formal definition for big O? That's the one with the constants. You may have seen it in 210. You may not have. That's okay. So let's write her down. So I'm going to have two functions I'm going to call f and g. In particular, they're going to be complexity functions. Let f and g be complexity functions. So we're going to say that f. Now, I want to stress one small technical detail with you. This is one of these small things that does matter if, say, you really want to get meticulous about this. I'm going to very often write what looks like f of n when I actually want to describe a function called f. Does anybody want to point out to me why this looks like an abuse of notation? What I mean by that is it may mean something else than what I'm actually saying. So I'm using this to describe the name of the function and what it is. Can anybody point out what would be a drawback of me describing it like this as being the function f? What does this also mean? So if I write down, so remember, f is the name of the function. This is the input. This is actually why I would like to write it like this. But somebody would tell you, Dan, this is actually an abuse of notation. But we very commonly do this in computer science and maths, very often, because we want to say what the input looks like. Does anybody know what this also means? What does that also mean? So remember, a function, it takes an input, and what's the output? What's the output of a function? It's this too, right? So somebody told you what's f of n? That's the output of a function f given input n. That's not what I'm saying right now. I'm talking about the function with input n. It's just an abbreviation, so I don't have to write all that mapping notation and stuff. Does everybody understand? Just to make sure I'm not going to confuse anybody. So I'm not talking about the output of a function. This is just the function with this as its input. Is that crystal clear, everybody? Give me 2 thumbs up if we're okay with that. Wonderful, wonderful. I have to at some point give you that spiel. So I've done it now. So I'm going to say f of n. Sorry, f is big O of g. So very often the reason why I say this is because often I will not say this part. So f is big O of g if and only if, so it means whatever I write after this is going to be equivalent to me saying f is big O of g. If and only if there exists. Now, some people will very often know that there's a simple way of just writing down there exists. Sometimes people like to use this capital backwards E for there exists as an abbreviation. It's also a symbol for logic. So I just wanted to point that out. There exists some positive real constant, C. So there's going to be two constants that we're going to have to keep an eye out for. And a positive integer constant, and 0. So these are going to be our two main constants we're going to have to really pay attention to. So just keep in mind these two constants are a thing. Such that for all. Now some people like to abbreviate for all with an upside down capital A. You may have seen this if you studied a little bit of logic. It's a quantifier. For all n greater or equal to n0, then this is what I want to have happen. I want it to be that f of n, now I'm referring to what the value of it will be given n, is less than or equal to c times g of n. So I want to kind of give you just, because this is a lot to digest if you've never seen this before. Is there anybody that's never seen this definition before, or something like this definition? Now, I will give you a heads up if you remember way back, maybe to some calculus even. There's a definition that's quite similar to this one. You may have seen it. It's called a limit. It's quite similar to this one. It's not the same though, but they're quite similar. This is a little different. But there's two things I want to point out for you that I really want you just to imagine. Is think of this like a game that you're playing. So I'm given these two functions, f and g, and the game plan is I need to show that there exists this constant c, that's a positive real number, constant, and this other constant, n0, and it's a positive integer. It means it has to be 1 and above. It can't be 0. Such that when I have these two constants, this inequality has to be true for all points after and including n0. So let me just kind of give you the bits and pieces that should connect to the intuition I gave you a little earlier. So you look at this constant and say, okay, well, Dan, like, why do we care about this? Well, did you see what I did over there? I had all those constants kicking around. I would like a very natural way to, regardless of what those constants might look like, I want some way of talking about the two functions. So that's one intuition I want to give you. And those constants can be different between different machines, right? Likewise, you can think of this n0 as that trade-off point I was referring to earlier. Does everybody see that? That's a very natural intuition, I think, for this definition. There's several other ways you can intuit this definition, some more formal than this one. But I think this hopefully helps motivate why Big O is a rather useful definition for describing algorithm running times. So I want to talk a little bit about usage because we're going to use Big O and these other notations quite frequently. So let's talk a little bit about this. So I must stress that when somebody reads this to you, they'll say f is Big O of g, or they'll say f is in Big O of g, or they'll say f is of order g. So these are very common ways of referring to what I've just described here. Now I want to give you some notes about usage. I know that you'd be like, Dan, why do we have to talk about this? It's very important because I want to make sure that when you leave this class, if somebody else describes Big O notation a little differently to you, or say you're trying to look into something more technical and you come across some weird symbols, I know I've told you a little bit about this and different ways we can use this notation. So I'm hoping this will justify this reasoning with you. So I'm going to say, so f is Big O of g is written a couple different ways. A couple different couple different ways. So I'm going to give you a couple different ways you can use big O notation. Now, if ever it's unclear to a reader, you could always just say F is big O of G. And they'll know what you mean. It's not, there is no confusion. However, I want to talk about how we can use this notation, because there's actually a couple very natural ways to interpret big O notation. One is more what we call set theoretic, which is technically more formal than the latter. The latter is very useful when you're trying to sum up or use big O notation when you're trying to do calculations. So I want to show you both of these so that you can see which ones maybe make a little bit more sense to you if you ever want to use this. Or if you, just to give you a flavor for how you can look at these two things and say, okay, that kind of.
A few moments later.
But no, this is a very, I've never had this happen to me before during a lecture. I've had it where the power went out, but never like this. This is a very, I would consider yourself very lucky. I usually consider myself rather prepped for these things. Anyways, let me just get the chat back over here. Okay, as long as I'm still clear, and I'm hoping I'm not clipping or anything for you, because I don't want to make the ears or any part of you feel uncomfortable, okay? Okay. Either way, let's just hope we have a little bit of fun with this. I'm hoping that the recording, it won't sound like this. Or maybe I do. I don't know. Anyways, let's talk a little bit about usage and cross our fingers that we don't run into any other issues for the rest of the lecture. Okay, usage. So very often when somebody wants to say is, they often mean is in. So if somebody tells you F is big O of G, they might write it like this. And this means in set theory. Or is in, if you really want to go meticulous with this. So, you might ask, Dan, where does that come from? So what I'm saying is that big O of G is actually a set of complexity functions. It's actually a whole set of them. Is a set of complexity functions. So if you really wanted to write this out very technically, you could write it like this. Big O of G is a set containing complexity functions f such that there exists, so that's that backwards E, there exists C, which is a positive real constant, and N0, which is a positive integer. That's what these pluses mean. So remember, that's the set of all real numbers, positive, set of all integers, positive. And then I'm saying for all, remember that means for all. N greater or equal to N0. And then you can say f of n is less than or equal to c times g of n. Sort of squishing in there. But here's a set. This actually contains a whole bunch of complexity functions. And oftentimes this is a really useful way of looking at big O. I'm going to give you an example of what I mean by this in a little moment. This is one way you can interpret big O notation, by the way. So when you talk about different big O's, like big O of n and big O of n squared, you can actually think of them as sets of complexity functions that you can actually organize by their containment of what functions are in which sets. Just think of it like buckets. Here's another one. This is one that you'll very often run into in your studies. I'll tell you that up front. So some people will write is as an equal sign. It's a convention. So where that equal sign means is. It's not equals. That's not what it is. Just to be very clear. So this is a very common convention for when you want to write out and simplify calculations over big O terms. It's very commonly used in analysis like this. So let me just, so I'll say often this usage is helpful for simplifying. For some reason I can't spell at the moment. Simplify for simplifying. This says simplifying, by the way. You either put that in bold. I'm just joking around with you. My apologies. For simplifying calculations. So if you have many, many terms with big O, what you could do is you could do something like this. So suppose I have f. So suppose I give you f, and that's going to be equal to 8n squared plus 32n plus 20. Now, if you know a little bit about big O notation, you can drop the constants I have here and these multiplicative factors. They're all constants. But which term here is the dominant term? Which one has the highest degree as a polynomial? It's this one, right? So if somebody told you right here, what's the big O of all of this? They might use this equal sign, which you read as is, and they would say, okay, it is big O of n squared. And here's some more. Okay, so here's G. Say if I say 4n cubed minus 2. I might write this and say, okay, 4n cubed minus 2 is big O of n cubed. So far, this seems rather like, okay, that's just a symbol there. It's nothing too particularly special. Let me just throw another one in here. Suppose I give you 8n. You'd say that this is big O of n. So what happens when you have f, g, and h and you add them together? So this is where the notation becomes rather useful. So suppose I give you f of f plus g plus h. Now, each of these terms here, we know each of those is a function, and each is a big O of a something. So what I'm going to do is I'm just going to write each one of those in terms of their big O. So I could just say, well, f is big O of n squared. G is big O of n cubed. And h, that's big O of n, right? Now, for those that might look at this and say, Dan, that's a little odd. Did you just say, like, big O is a set? That's why I'm saying that this is rather more informal. Is that I'm technically adding sets of functions right now, which seems very nonsensical. But this is one common usage in analysis with big O notation. Now, if you looked at this, what would you say would be the outcome of this calculation? Which is the term, just like I did over here, which one has the dominant term? Is it going to be n squared? Is it going to be n cubed? Is it going to be n? Which one is going to be the big O term here? Yeah, it's just n cubed. So I could just say is big O of n cubed. Now you might ask, Dan, why are you showing me this? Well, here's the cool part. Okay, suppose that this is one part of your algorithm's running time. This is another one, and this is another one. And you want to determine what the overall running time of your algorithm is? Well, boom, boom, boom. Each of those has a big O, and I'm just simplifying. Does everybody see how that's rather handy? So if you have many steps to your algorithm, like say you have like 2 pieces to them, all you have to do is analyze your pieces that you're interested in, and then you can combine them together, and this notation gives you a very simple way of writing that down. Is that kind of cool? So I just wanted to show you this. This is rather interesting uses for big O notation. So is everybody okay with this? I just wanted to show you how couple different ways you could use big O notation. If you want to be a purist, sometimes like me, I usually stick to this definition up here, but you'll find that when you do calculations offhand, this was a really helpful one, or if you use it on like an assignment or something. It's really useful. Okay, so if we're okay with this, I'm going to proceed to now kind of connect the pieces, because I want to show you really why this first interpretation is rather useful for us. So I gave you some motivation behind the second one. So once we do that, we're going to start playing around with these definitions. Okay, so I want to come back to why would we use asymptotic notation to talk about algorithms and comparing algorithmic running times. So I want to go back to our search problem. Let us go back to our search problem. So I'm going to make a further assumption. Assume the input array is sorted. So meaning I'm considering a special case of the search problem. Just to be rather technical with you. So, can somebody tell me 2 different algorithms I can use here? We already seen one of them earlier today. So I'll just say that one. We have a couple different algorithms we can use for this case. We have linear search. What's the other one? It starts with a B. Starts with a B. And it's not balloons. Binary search. Very good. Binary search. So we know that the worst case time complexity of linear search is big O of n. You may know that the worst case running time of binary search is big O of log n. If I want to be particular, I could write the base 2 there. Doesn't matter. Believe it or not, with asymptotic notation, you can get away with not really caring about the base. So, suppose that you went through this process we did at the beginning of lecture, where I derive a complexity function, and so on. Suppose that that complexity function that I derived in my analysis, I call it, say, T1 for the linear search. And you would agree with me with my analysis, based on what we said earlier, that T1 would be in big O of n, right? Now, if I came up with another function, suppose this is I do the process with binary search, and I come up with another complexity function. I'll call that T2. Well, T2 is big O of log n, so it means that T2 is in that set of functions that are in big O of log n. So, if you were to derive these, and you count up all those operations, here's a fun picture to really kind of help put this all together. Now remember, when I did this, I had those constants, right? And there can be many, many, many meanings for those constants. And they may represent, for example, like I said, actual CPU cycles. And those could differ between different computers. So here's a picture to really help kind of really give you an idea of why we might care about this. So here's my first blob thing. This is going to be big O of log n. That's my first blob thing. Then the outermost one's going to be big O of n. And inside of the innermost one, you're going to find a variety of functions. You're going to find, for example, log n. You might find T2 of n. So you might find T2, you might find log n inside here. There's many, many functions that are going to be in here. Likewise, outside of there, you're going to find n. You're going to also find T1. And there may be several other ones there. But notice that all of these are well contained within big O of n, right? They're what we would call a so this set, which I've represented as this blob here, is actually a subset of the bigger one. And remember, if you think about it like I did earlier about all these constants could represent many, many different cycles on a computer, for example. It's like your CPU cycles, or just generally, they could be almost anything as long as they're constants. My point is that they're all in big O of log n. Likewise, if I take linear search and I look at all possible sets of constants that may be represented by T1, they're all in here, right? But they're not in here, right? Does everybody see that? They're not in here. They're out here. So when you look at this picture, the set big O of log n contains complexity functions, for every, now this is the part that's going to hopefully will blow your mind a little bit if you've never seen this before. For every implementation of binary search. That says set big O of n contains complexity functions for every implementation of binary search. So remember, all those constants, if we take our machine-dependent view of everything, your computer will have different constants than a different computer will have, right? So if I were to give you, say, a C++ program, for example, that implements binary search, well, would I run on somebody else's computer or yours or mine? Maybe not on mine, my power might go out. Each of them are going to have different constants, right? So that means all of them are going to be in here, right? Including all the other ways of implementing binary search. Isn't that wild? So this gives you a categorical way of talking about over all possible implementations, if assuming they follow the rules of our model, that I could tell you that binary search is more efficient than linear search. Isn't that wild? It's really interesting. So I'm just going to say we can conclude binary search. That's a C. Let me fix that. Binary search is more efficient. I'm going to say EFF, more efficient than linear search. But does everybody get the idea? Are there any questions about this? I'm hoping that I've motivated why we might use big O notation, maybe in a way that you may not have seen in 210. So you can see that still, just to be very clear, for certain implementations, like if you need a very specific implementation to work better, use an experimental approach and optimize, for example. But if we want to talk about the algorithms more broadly, regardless of their input sizes, this is a rather nice way of categorizing them. So question, is the idea here that because binary search is within linear search, that it's more specific and therefore better? Now, let me be a bit narrow with this. Okay, so remember, we're looking at the worst case time complexity of these two algorithms. So notice that what I'm saying is that when you go through the process we've been doing for the last while, where I counted up all those operations, if I told you that that's T2, T2 most certainly is in the set big O of n. But the thing that's interesting is that if I were to do this with linear search, I could tell you that it's not inside this bubble, the one inside here. And that's regardless of what those constants are for sufficiently large n. Remember this whole trade-off business where that n0 exists? There's going to be some point where this trade-off occurs. I don't know where it is, but it may exist. It always depends on the complexity functions themselves. But the whole idea here is that by categorizing our problem and our resources or complexity necessary for solving the problem, we can now talk about how all of our measurements of the running times, we can actually put them in bubbles like this and categorize them like this. You could go even further than this, actually. You could actually look at a problem itself and categorize it by its efficiency of how quickly you can solve it. But we're not going to go quite there yet. But does that clarify really what I'm trying to illustrate here? Is that, remember, like when I did the table exercise last day, where I had all those constants and I counted up all the lines, you can do the same thing with like grouping all the operations themselves, believe it or not. So each one of those has its own set of constants, and if you were to pick up any one computer, those constants might be different. The big point here is that they're all in here. They're not out here. But hopefully that helps a little bit with it. Is that crystal clear? Just want to make sure I'm not confusing anybody. It's one of those really interesting ways of thinking about big O notation. That's why very often when you run into big O notation, it's not really about like, okay, when the array is only length 10, I find that this algorithm does better than the other algorithm. It's not about that. You can most certainly have real conversations about those things at a performance level. What we're actually talking about is, given all the instances of the problem, remember there's infinitely many of them for most problems you're ever going to encounter. I'm trying to categorize which algorithm is more efficient than the other. So that means that there may be instances that are really, really big. So big that I can't imagine them. And that's why this is a rather useful way of thinking about big O. Big O is a tool for us to categorize like this. And there's other asymptotic notations we could use to also categorize just like this way. But yeah, no. So, are any other questions about this? And keep in mind, I'm going to do some examples where we're actually going to prove some asymptotic properties, okay? So don't worry, we're going to be doing that. I just got to lay out some more definitions for us so that we can start playing around with these, okay? I know I'm laying on those definitions just like I'm spreading mayonnaise on a sandwich. So why don't we do that? And I'm hoping we'll have time to do an example. But if not, we will definitely do some more on the next class. But the outage sort of ate up some of our time. So let's do this. So there's a few other asymptotic notations I want you to be aware of. So one thing that you might know about big O notation is you could think of big O notation as an asymptotic upper bound on running times for algorithms when we use it in this setting. So that means that for sufficiently large inputs, it's going to serve as an upper bound on the running times because those constants are going to become almost negligible. You're not going to have to worry about them when the input size is that big. You might think of it that way. That's most certainly a very useful way of thinking about it. I'm hoping to talk a little bit more about some other notations for us. We're going to talk about a couple others. You may have seen these before. I'm going to lay out their definitions as well. So we're going to talk about big omega next. So I told you that big O is like an asymptotic upper bound. And the easy way to remember that is that if you look at the inequality that's in the definition for big O, it's a less than or equal sign. And we look for two specific constants. In big omega, believe it or not, all I'm going to do is I'm just going to give you the same definition. I'm just going to flip this inequality. Just keep an eye out for that. So I'm going to say F is big omega of G if and only if there exists constants C. So remember, we're going to have a C and an N0 just like before. So I'm just writing this a little bit more briefly as opposed to using full words because the definition is going to be almost identical. So that for all n greater or equal to n0, it's that f of n is greater or equal to c times g of n. So I have a very down-to-earth question for you. If big O notation is an asymptotic upper bound, what is big omega? Just think about the inequality over there. Yes, lower bound, asymptotic lower bound, perfect. So very often when we use big O, you'll find I will very often use the verbiage of at most. Whenever I talk about big omega, you'll see I'll often will use it in a way that I'm referring to things as at least. For example, if I wanted to talk about the running time of an algorithm, I'll tell you, oh, it's going to take at least this much time. And that's very commonly how people use big omega notation, is they talk about at least this much time. We'll see an example of how we would use this kind of notation when we start talking about lower bounds. Now, I'll give you a tip. If you find yourself looking at this definition, you're like, it's another definition. Here's an easy way to remember this definition. Here's a tip. If somebody tells you that f is big omega of g, this is true if and only if g is big O of f, which naturally matches the intuition I gave you, right? All you do is you flip them around, and then you now have a statement about big O. Does everybody see that? Now you might ask, how does that pop up in this definition? Well, think about it. If you divide both sides of this inequality by c, so you divide this by 1 over c, and you take 1 over c on both sides, notice that this will become g of n is less than or equal to 1 over c times f of n, which, if you think about it, 1 over c is another constant. It's a positive real constant, right? That's how it happens. It's kind of neat, but this is a nice, helpful cognitive shortcut. If you find yourself doing these if you run into big omega, just flip the two around and see if it makes sense. Okay, another one that you may have run into is called Big-Theta. So we say that f is Big-Theta of g if and only if. Now this is the best part, is that if I have an asymptotic upper bound, like big O, and I have an asymptotic lower bound, I would like to have some way of describing things where it's asymptotically tight. As in, the asymptotic upper bound and the asymptotic lower bound, they meet. They're tight. That's what Big-Theta is going to be. So naturally, you might guess what the definition of Big-Theta will be. If and only if f is big O of g and f is big omega of g. So it has to satisfy both of these. So it has to be that g is an asymptotic upper bound and that g is also an asymptotic lower bound. Does everybody see that? It's rather useful. Now you might ask, Dan, why would we need this? We've been using big O notation for a good while. I'm going to show you a very concrete example of why. Okay, if you were to play and use the definition of big O, we know that binary search, for example. So if I give you binary search, when you and I talk about this, you tell me that the worst case time complexity is big O of log n, right? For binary search. You've seen this before, right? Well, as I told you, big O is an asymptotic upper bound, right? So, with the power of the mayonnaise, I can also write that binary search's running time is big O of n to the 99. Now, is that accurate, though? is this an accurate way of saying the running time for binary search? Would you say, hey, look, binary search runs in big O of n to the 99. End of day, I'm going to go have a nap. Okay, maybe on a rough day, but I would not advise doing it. So this is where Big-Theta becomes very useful. Because you can say that the running time of binary search in the worst case is Big-Theta log n. But you cannot say that binary search's running time is Big-Theta of n to the 99. You can't do that. It's wrong. Because what will happen is, you want to know why that would fail? It's because it would fail to this big omega definition. Because it would say that my algorithm requires at least big omega n to the 99 operations to execute. Which, no, that's not what happens, right? So that's why Big-Theta is a very useful definition for us. So almost always when you run into analysis for algorithms, like in 210 in previous courses, when people talked about big O notation and they said, oh, it runs in big O of log n, they normally did it under the tightest circumstances for the analysis. So almost always when you ran into big O notation, when somebody wrote down the running time for you, they actually meant Big-Theta. Boom. Just the thing is, it's a stronger definition. It requires proving two things. So most of the time when we do our analysis, I'll just assume that you can carry out the other side of the analysis if we use Big-Theta. Okay? Is that clear, everybody? So that's what Big-Theta is. So I want to give you two other definitions. These ones, we're going to run into them, but not very often. One called little o. So I'm going to say f. F is little o of g if and only if f is big O of g and f is not. I'm going to put a cross through the set theoretic in to say not in. Not in Big-Theta of g. Now, coming back to my analogy I'm drawing on these inequalities, you could think of big O as an asymptotic upper bound. You could think of big omega as an asymptotic lower bound. What little o's definition is there's a much more fancier way of writing it out. I'll include it in the notes. But for most purposes in this class, you will never need to use it. Here's the idea. Well, we know this is an asymptotic upper bound, right? This is saying that it's of the same order, but it's asymptotically tight, right? So what this is saying is it's an upper bound asymptotically, but it's not tight. So if you think about it in terms of my analogy over here, it means that it's a strict upper bound on the running time. So just as an example of using this, you could say that n is little o of n squared. But n is not little o of n. So you can think of it as a strict upper bound, asymptotically speaking. That's what little o is. You think of it as a strict upper bound. It means it has to be something much bigger in that little o, at least. Is that clear, everybody? Here's another one. It's the same idea, just the other way around. It's called little omega. Naturally, it's a very cute little omega. Looks so cute. Look how cute that is. Sort of melting, because I kind of drew it like it's in a microwave. So we say f is little omega of g if and only if f is big omega of g and f is not Big-Theta of g. So you can think of this as a strict lower bound. So it's the exact same idea I just gave over here, but the other way around. So anyways, everybody, I hate to stop it here because I want to do some examples. So when we come back next time, we're going to do lots of examples going through big O, big omega, and big theta and applying these definitions to see how we can prove these kind of claims. So that being said, I want to say thank you very much, everybody, and have yourself a beautiful day. I'll stick around for any other questions. I'll see you later.